Great. Thanks very much, Tristan, and thank you very much, Prague, for having me. It's always lovely to be here. I like this video a lot. Uh, and today I'm going to be talking about how to get around this problem that Aaron was describing, which is that you have a groupoid homomorphism, the kind of natural arrow between two groupoids. It's not clear at all whether it should live to the C star level. So the problem is partially that groupoid homomorphisms, that is, continuous functors, if you view these as small categories with that are topologized with inverses, but just the set functions that preserve the structure relevant to the groupoid, like the inverse and the multiplication, and also are continuous. These don't lift in an obvious way to star homomorphisms on the C-star algebras because you have to be able to encompass both the group setting and the space setting. So these things generalize both group homs and continuous maps between spaces or topological spaces. And since one of these constructions is covariant, or one of the C-star algebra constructions on these objects is covariant and the other is contravariant, we run into this problem. So just to write it down again, if this is a continuous map between compact topological spaces, we build the associated groupoid C-star algebras, which is just getting the continuous functions back, and you get a morphism the other way via pullback. This is if X and Y are spaces. If if gamma and so that after gamma, delta. Yeah. If gamma and delta are, say, discrete groups, and you have a group homomorphism, then you get a group homomorphism or a C-star homomorphism in the same direction by a kind of push forward construction. And so having to deal with this going forwards and backwards at the same time requires you to have a little more elegance of the definition or kind of morphism that you consider. There are some groupoid homomorphisms for which you can do this, and the obvious example is if you have an isomorphism of groupoids. So a groupoid homomorphism that is itself a homeomorphism will then give you an isomorphism of the resulting C-star algebras, but this is a very restricted class. And there are some other things you can consider, like open embeddings of groupoids and these continuous proper fiberwise bijective surjective maps. But they both somewhat fall into the same category, well, not category in the technical sense, but bucket of what I'm about to describe. So instead of considering groupoid homomorphisms, the traditional kind, we consider a different kind of morphism between groupoids. So this definition goes back to at least Bonecci and Stakura, who credit it to Zhakhshevsky. I don't know, I think Zhakhshevsky used it in a very particular context, and then Bonecci and Stakura gave a more general groupoid definition. I don't remember the exact history. Do you know, Tristan?
Yeah, I'm not sure. Just talk about it and like you need the whole thing, but yeah, I'm not sure quite exactly.
So I'll write a bunch of names down here to cover myself. And the current terminology that I use comes from Maya and Zhu. So I use just standard Roman G and H for my groupoids because I'm lazy, but these will be some groupoids. the étale groupoids, and much to I'm sure everyone's disappointment, I'm going to assume that my groupoids are locally compact in Hausdorff. Just for the purposes of the talk, you can do this in the non-Hausdorff setting and parts of it in the non-locally compact setting, but I think you still get a lot of the benefit, or you can get a lot of the content of this talk considering only the Hausdorff setting, and then think about the non-Hausdorff setting if you decide you want to do that later. And I'm happy to chat about it as well. But for now, we just assume, I'll just put the blanket assumption of Hausdorffness and local compactness. So two étale groupoids, an actor from G to H consists of following data. So we get a continuous map row that goes from this codomain groupoid into the unit space of the domain groupoid. So from H into the unit space of G, and a map from the pullback, and I will write down explicitly what this set is. So a kind of a subset of pairs of elements from G and H that goes into H, and these are exactly the pairs of an element in G and an element in H, such that the source of this element of G matches up with the row image of this element of H. And then, well, how should this map look? I haven't given it a name, but I'll write gamma x pair gets mapped to gamma times x. And it should satisfy some conditions. Firstly, is that rho of x times x is equal to itself, or is equal to just x, and the idea here is that rho of x is something in the unit space. The idea is to mimic something like a group action, but for a groupoid version with some extra compatibility. So a unit should act by doing nothing. If I take the image of one of these products, gamma times x, under this row map, it should be just the range of gamma, where, well, so this is gamma x, a composable pair. So it's just x and h. That's what happens if you look at the left. If you look at the right, you should just recover the source. When you look at the source of this product, you should recover the source of the guy on the far right. So if you think about if you're composing arrows or composing functions or morphisms in your favorite category, the thing on the right, the source of the whole composition, where the arrow starts in the whole composition, should be the same as just the very first arrow, the thing on the right. Then,
I'm just confused. Rho x times x.
Yes.
X. X.
So x is an element of H. So rho of x then lies in G0,
Right.
which is inside of G.
Yes.
And we can apply this map, this multiplication map, because if I have an element in the unit space and I take its source, I just end up with the same thing back because it's a unit arrow. So the source of this guy will be equal to the row of it. If I have that, I just get rho of x back. This map row is called the anchor, so if I say the word anchor, that's what I mean. But the source of the anchor of x is just the anchor of x again, which means that it is one of these pairs that you can apply this map to. Okay. One possibly helpful example is if G is a group, this will reduce, or part of this will reduce to just being a group action. And when you have a group, you want or group action, your identity element should act by the identity, and that will be exactly this guy. So also to mimicking the group setting, if I have a composition that looks like that, then I should be able to shuffle my brackets around however I like. And this is for gamma and eta in G and X in H. And this is where I introduce a little bit of terminology, WTMS, which means where this makes sense. So these maps are partially defined, so this isn't always a sensical equation, but when it does make sense, it should hold.
Or should be to access the exactly group reductions spaces.
So far, but I'm not done.
Oh.
Yeah. Now the first four of these make this a groupoid action. Actually, I think without this third one, but the fifth one is really what makes it an actor. Now, this is saying that if for an element of the domain groupoid and two elements in the codomain, such that these compositions make sense, they should agree. And this is saying that this left action of G on H should commute with the right multiplication of H on itself. So I can apply the left action first and then the right multiplication, or I can do the multiplication ambient to H and then apply the left action. These two should coincide. Quick example, if gamma acting on X is a group action on space, where gamma is just a discrete group, then we can build a groupoid out of this action, which consists of, as a set, it just looks like the product with source map. We'll just be picking out this second coordinate. The range map of the pair will, instead of picking out the spatial coordinate, I'll apply the group element first, actually, because I'm in a discrete group, I'll call this G. And then the multiplication is defined for pairs of the following form. This is one of the main examples of a groupoid that is not consisting purely of space or just purely a group over a space, but rather it has some kind of dynamics. So this is the transformation groupoid. Associated to this action.
Can I ask a quick question to your groupoid action definition here? So thinking of the category theory picture, where we said that here the groupoid would be like a small category with all morphisms being isomorphisms. What would be what is the corresponding counterpart of a groupoid action there? So is it like a functor between those?
It's not a functor between the groupoids. It is. You need at least if you know what a groupoid action on a space is, then you can build a similar thing to this, where you have instead that transformation groupoid, and then you need a functor from this transformation groupoid acting on this space to H that fixes the unit space of H in both cases. There is a way to frame this a little more categorically, but I'm not sure it'll be helpful because you already need to know what a groupoid action is, which involves this anchor data.
I think, I mean, Strakuros, but they were sort of formalizing this in a slightly different way using relations between the groupoids. And there, I think, really is a kind of functorial relation in the sense that, you know, the multi-linked things, these two things, the relation holds them. That's the product. So yeah, it is kind of like a functorial relation rather than a function.
Yeah.
If that makes sense.
Okay, and then the extra condition here would be yet another thing that you asked, or
So all those conditions can be translated into these functorial relations, although it's not immediately clear to do this. You have to do it before you. But yeah, I mean, I can talk to you about later.
yeah.
I've forgotten how exactly they do it in the Manchester Cooper paper, but this is the way it's phrased. Or this is the unfolded version of the way that Ravman and Chen Changzhu phrase it in their paper. They do it a lot more succinctly by just saying it's a left action that commutes with the right action of the codomain groupoid on itself. I decided to unfold it a bit more so that people would have a chance to follow it. So we have this transformation groupoid, and this admits an action of the group gamma on it, or an actor of the group gamma on it. The anchor map has to go into the unit space of a group, which is just a point, so that is automatically determined. So there's no data there. And the product, the product of the actor becomes defined everywhere. So this. So I have G and then here HX. How should I multiply these two things together? G dot HX should exactly be just multiplication of the first variable. And although not every étale groupoid has this form, a lot of them do. Like a very, very big, interesting class of them. The people in classification program, the Caesar algebras at least, are considered this. And this groupoid, or this transformation groupoid encodes and recovers all of the structure of the original group action.
So what do you mean precisely by a large class? Like, can you characterize it somehow?
Large in the sense that people are interested in them.
Okay.
Not large in the sense of like if you threw a dart on the dartboard with all groupoids, would you get one of these? Actually, they're rather small in that sense. But you'd get, there's a slightly more general version of the transformation groupoid, which does give you all étale groupoids using inverse semigroups instead of groups. But this one is a bit easier to frame and requires less quotienting by weird things. Okay. So one last thing we will say, an actor is proper if its anchor map rho is proper as a continuous function. Once you restrict it to unit spaces. So if you look at this anchor map, it originally goes from the whole group, like whole codomain group, or just to the unit space of G. But if you just look at what it does to the unit space, if that's a proper map, then you say that the actor is proper. So this is as in after restricting to H0. the reason I make this restriction is that when we lift to, I'll show that these guys lift to C star or homomorphisms between the groupoid C star algebras, and in the commutative setting up there, the reason that Aaron originally assumed that X and Y were compact spaces rather than just locally compact spaces is that you would need to then add that this function is proper. Otherwise, you don't get a map between the C star algebras of locally between these guys. You would only get one from there to the bounded functions on there. So that part is if F is proper. So one version of this was done by Ramesh and Stakura, and then I adapted it to make it work in the non-Haskell setting. It wasn't really that much to do, but there were details that needed to be clarified. But this H, the actor for a function that is continuous compactly supported on G, there is, and another function that is continuous and compactly supported on H, there exists a function which I call phi of F juxtaposed with G, again in the continuous functions on H, satisfying I should say that this phi or this data comes from the actor itself. I want to take this guy, I want to evaluate it at some point in X. And do a very similar formula to what Aaron showed us with the convolution product within the, this guy by itself, but I'm now incorporating the action and using that product instead of the product in the ambient groupoid. Now, if you look at this, squint slightly, shift your head a bit, and then, or tilt your head a bit, and think of G as being equal to H, and this actor multiplication just being the multiplication of H on itself. This is just the multiplication in the star algebra of this guy that we would then complete into the reduced C star algebra. But now this gives me a way of actually taking a function on F, or on G, sorry, a function F on G, and multiplying it with a function on H. I now have this kind of product between the two things. And in fact, the formula sending F to IH of F gives a star homomorphism. Well, I guess I have to be slightly careful here. From the C star algebra associated to G to the multipliers on the C star algebra associated to H.
Those are full.
Those are full.
Yeah.
Yeah, so we didn't talk about it yet, but there is, you can do this construction of the reduced groupoid C star algebra. There is a construction of a slightly larger one, or slightly / extremely larger one, which is just taking the completion of these guys in the maximal C star norm possible, which by doing some kind of L1 type estimates, you can show is actually bounded in the first place, so it exists.
So how is phi H of F without the define?
You don't have to define it without the G because you're defining it as a multiplier on these guys. So you define it firstly as an operator from this guy to itself. And so in order to define the operator, you just define what it does at each element of CCH and then show that it extends.
Okay, right. Sorry, okay, so I'm just confused. This not a subscript. What is it?
That's the little h.
The little g.
Which one?
The g in the square brackets with the g.
Oh, no, that is a
Okay, right.
full-fledged.
Right.
Yeah. So this guy becomes that.
Yeah, okay, I got you.
We also should be real now
Hmm?
in
Where?
the formula.
Ah, yes. It should be right.
So maybe G is not great at it, maybe using the group way.
Well, G is exclusively either a function or a group element. It's never a group element. Yeah, so I could do like F1, F2. If it comes up again and bites me in the ass, then I'll live, hopefully. So we have some way of getting into the multipliers in C star H. And the reason I introduced this properness is that this is exactly what tells you that it lands in the subalpha. This thing contains that C star algebra in a canonical way. And if H is proper in the sense just there, then the entire image of this phi lands in there. So we get a map from C star G to C star H.
Oh, so this is like there's a dot behind star H, like the formula gives star homomorphism period, and then if H is proper, then it's not that it gives star homomorphism if H is proper.
Ah, yeah, sorry.
Okay.
Yep. Thank you. So the properness just ensures that you land in the C star algebra itself rather than just in multipliers on it. So this is this kind of like spatial component where if f is not proper, when you pull back a function on y to a function on x and along a non-proper but continuous map, you might not get something that's compactly supported anymore or vanishing at infinity. You might get something that's just bounded. And that sits in the algebra of bounded operators on there, but not in the algebra of vanishing at infinity of, not bounded operator, bounded functions on there, but not in the algebra of vanishing at infinity functions. Keep wanting to say operators. So this at least gives you a way to construct a star homomorphism. But does it answer this question about functoriality? Okay, is the process of building the groupoid C star algebra functorial in some sense? The answer is yes to this, but in order to say or even talk about that, I have to say what the composition of two actors is. If we want to talk about this category of groupoids with actors as the morphisms, we need to be able to compose things. Otherwise, we're talking about a directed graph, maybe. So, if H, little h is an actor from big G to big H, and little k is an actor from big H to big K, so G, H, and K are volatile groupoids, and I've got two actors where the codomain of one is the domain of the other. Can I compose them? Yes. KH from G to K with, well, I have to specify the anchor. I need a map from K to G0. I have a map from K to H0 and then from H0 to G0. So the anchor associated to this product would just be the composition of the anchors, and if I do this in the right order, yep. So this is the map from K to G0. And then the multiplication takes an element or a pair. What symbol do I usually use for this? Forgotten. Let's use the new. How do I multiply two things? Well, the idea is that if I multiply by a unit in the middle, then I shouldn't change anything. So I'll just take that to be my definition. Okay, so I know that nu is equal to the anchor of nu times nu by this this axiom. And then I also need to be able to shuffle brackets around, presumably. And this is an element of H that I can act on with gamma. I just take that as the definition. This is an expression that makes sense because this is just incorporating the first actor, H, and this one is the actor K. You can show that this gives you an associative composition. It's essentially associative by design because I can put all of these, I can put the brackets wherever I want. And it has units because you can show that the left multiplication of a groupoid on itself gives you the identity actor in the right way. This composition turns groupoids with the necessary adjectives and actors into a category. There. And then show one of the other important results that Bonecci and Sakura proved, which then says that this construction that sends a groupoid to its C-star algebra, its full C-star algebra, and an actor to the induced, or say a proper actor, this is a functor. That is, if I have a composition of actors, K and H, like here, and I look at the star homomorphism associated to the composition, this is exactly the composition of the individual star homomorphisms you get from the actors K and H. The proof of that runs basically the same way that the proof, or as the proof that's the convolution product in the groupoid C-star algebra is associative. The reason for that is the formula for this multiplier that we induce is essentially this, looks very much the same as the convolution product in a groupoid C-star algebra. So you just run the argument again, but instead of proving associativity, you're proving a different kind of bracket shuffling. You get the same positive result. But to quote a mentor of mine back in Australia, associativity should only ever be proven in the privacy of one's own home. So I won't do it here. It's also an absolute tiny sin.
Was that Aiden or Adam?
That was Adam. I think Aiden might just groan if you asked him to do it. So this is at least part of an answer to this question of can you lift something from groupoids up to the C-star algorithm in terms of morphisms that isn't just yes, isomorphisms work. And in fact, you can show, now that I'm mentioning isomorphisms, if you consider this other category of groupoids with actors as morphisms instead of groupoid homomorphisms, you might ask, do the isomorphisms change? And the answer is actually no. If you have an isomorphism or an invertible actor in the category theoretic sense, then it must actually come from an isomorphism of the underlying groupoids. So you don't create extra isomorphism classes or change the isomorphism classes of the groupoids in this way, you keep them the exact same. So, still got this nitpicky problem of having the full groupoid C-star algebras around here instead of the reduced. And the question might be, well, how do I get to the reduced ones? Do I need a condition on the actors? Well, what I'm going to give you is not a necessary condition, but it is certainly sufficient. So we say an actor is free if gamma times x equals x implies that gamma is a union. So if you think of a group action is free if the only thing that acts like fixes an element somewhere is the identity. The groupoids we require roughly the same thing, except instead it's the identity, I say it's an identity. So this is a non-triviality condition on your actor, a strong one. But if H is free, then the map on the full groupoid C-star algebras actually goes down to the reduced ones as well. And this is because partly because you can write the reduced groupoid C-star algebra as a quotient of the full. That's the sense in which the full is bigger. So then you get lowercase I from the actor homomorphism doing the same thing. So this means. So this is just saying that on the dense subspace of CC functions in here, I use the same formula. The only difference is when I go to limits of these things in different norms, and then you have to check compatibility of the norms, or you would usually have to check compatibility of the norms. The way I get around that is a slightly different way, which is the other reason I actually insist on freeness rather than just whatever condition of the actors will give me this dissension. So,
but in this case, it is free, then will this be implemented by an actual functor then? Like
no.
No?
You get something akin to a continuous surjective five-wise bijective proper thing, but it's not from the codomain groupoid, it's from the transformation groupoid sitting in this way.
Okay.
Which requires this intermediate stepping stone groupoid when Shin and Soja did it, at least. Or actually, when you do it as well with this open inclusion, you consider this subgroupoid.
Yeah.
You have to do things on the level of the subgroupoid rather than the global groupoid.
Right.
Yeah.
And once you restrict the subgroup,
Then you get that, yeah.
then you get a function.
Yeah.
Okay.
Yeah, exactly.
So for this transformation robot example, the actor from the transformation robot, is that free and the actions free?
No, that one is free, full stop.
Oh.
And that's because it's acting on the group, not the space. The actor at least. So this, if I look at, where did I write it? Yeah. G actually acts on the group component, and the left translation action of the group on itself is always free.
Oh.
Yeah. So that's just independent of the.
Okay, but why do you define it like that? Like, isn't and like my first guess would have been to act
On both.
like, yeah, exactly. To
With the diagonal action. Yeah, that doesn't give you an actor, that would give you a possibly something in the realm of a double groupoid structure, which would be a groupoid internal to your other groupoid.
Okay.
I think there's a couple of papers floating around on some Caesar alpha, structure of Caesar alphas of these. I think Matthias Palms put on as one. There's been a little bit done. I guess if you're far enough north in the world, then that can happen. But yeah, so if you're free, then you actually descend down to the reduced Caesar alphas. And the reason you do this is because you have these conditional expectations on the level of the Caesar alpha structure. So we stated that conditional expectations exist, but we at no point specified what they are. This is not about to change. What I am going to tell you is that they are kind of down to a subalgebra. And so we cut down in the sense that on this on this dense subalgebra of continuous compactly supported functions on, say, this groupoid G, the way to restrict down to the unit space is by literally restricting the function to the unit space. And so you just take an extension of that, and that gives you these magical maps which are called conditional expectations. And freeness is equivalent to this guy, to that big phi intertwining these conditional expectations. And this tells you that, well, another alternative way to describe the reduced groupoid Caesar algebra is to say that it's the quotient of the full Caesar algebra that makes these conditional expectations faithful. And so by intertwining the conditional expectations, you intertwine the way that these quotients are defined.
So once you do this, you're not considering any more like covariant morphisms between groups, for example. That won't satisfy this condition, right, of the expectation
Between groups?
Yeah, between groups like
between groups, this just corresponds to injectivity. So yeah, an actor between groups just becomes a group homomorphism, and freeness becomes injectivity.
Yeah, so it's
it's rather trivial for groups. Yeah, it's the interesting stuff doesn't happen on the group side. So Aaron mentioned towards the end the Cartan subalgebras and Cartan pairs, and it's also in the title of my talk, so I should probably talk about them. If you have a Cartan pair, Renault's reconstruction theorem tells you that there is a groupoid and a twist floating around to reconstruct your C-star algebra. So if C inside of A is Cartan, then there exists, and in fact it's unique up to isomorphism, étale and effective groupoid G, and I will say now what effective is. So this says that if you look at all of the arrows with the same source and range, you take its interior, this is just the unit space. So principality was the one condition that Aaron brought up, which says that if you have two parallel arrows with the same source and range, and they're actually the same, equivalently, because you have inverse, you can compose one with the inverse of the other and ask that any arrow that starts and ends at the same point must be an identity. This is still a restriction on how many arrows can start and end at the same place, but it's not saying that there has to be none other than identities. It's saying there has to be topologically very few of them. So an effective, if you have an étale, so the reconstruction theorem says that there is an effective étale groupoid G and a twist over G, which I'm not going to define because it's kind of, I think I have like 10 minutes left.
I'm confused about the effectiveness.
Mm-hmm.
So you have the interior of the section be empty.
It should the interior of the set of isotropy, the set of arrows that start and end at the same place. All of the units are certainly going to be there.
Like it's not more than the units.
It's not the interior should be only the units. And
Okay.
you will at least contain the units because in an étale group where you can show that the unit space is always an open subset. So what's the reconstruction theorem? It says that if you have a Cartan subalgebra, then your Cartan pair actually takes the form of looking like a twisted groupoid C-star algebra, but if you forget about the twist part, it's like a groupoid C-star algebra.
What was the Cartan pair again? Sorry.
This was so this is saying that C inside of A is master, a maximal abelian subalgebra, regular.
But it was the Cartan subalgebra, right? So
Yes.
what is the Cartan pair?
Oh, a Cartan pair is a Cartan subalgebra inside of the two of these together.
Okay, fine.
So a pair is the C-star algebra and a Cartan subalgebra. So it's the possible, you can't just put the C-star algebra by itself because it's possible it has multiple non-isomorphic Cartan subalgebras leading to multiple non-isomorphic effective groupoid models. The uniqueness requires that you fix the subalgebra as well. So, what was that? The reconstruction theorem tells you that you can build a groupoid and some extra data on top of it. But the main thing is the groupoid here out of the algebraic data or C-star algebraic data of the Cartan pair. Now, you can ask if phi goes from A1 to A2 is a star homomorphism and C1 inside of A1, C2 inside of A2 are Cartan, and phi preserves all of the Cartan structure, the stuff that tells you how to build this groupoid. Can you build this star homomorphism from groupoid data?
Quick question.
Mm-hmm.
So the lowest inclusion and the lowest sec, that should be less.
Yeah, that should be. Yep. Thank you. So if phi preserves the Cartan data, i.e. phi of the subalgebra lands in the image of the subalgebra lands in the other subalgebra, a normalizer gets mapped to a normalizer, and what else do I have? I have these conditional expectations. I should intertwine these. E1 and E2 are the conditional expectations associated to each pair. Does phi then come from some groupoid data, the data that we've introduced so far, an actor? So this question, as I've stated it, the answer is yes. But in order to prove the exactly as stated, I would need to be able to talk about twists as well. So instead, I'm going to tell you about the non-twisted setting, which is restrictive, but you still get a good idea of what's going on, hopefully. Yes. So if I take effective Attal groupoids G and H, effective actually is the exact condition you need on a groupoid to make this inclusion a Cartan pair. So what I'm saying is that the inclusion of the functions on the unit space into the reduced groupoid C-star algebra will be Cartan, and I don't need to twist. So that phi from C-star reduced of G to C-star reduced of H be a non-degenerate, and if you're not familiar with this term, think unital star homomorphism with that maps normalizes to normalizes and intertwines the conditional expectation and reserves the subalgebra. So if I have one of these star homomorphisms that intertwines all of the Cartan structure, it preserves all the Cartan structure, then there is some actor that recovers it. There is an actor H5 from G to H with phi is just the star homomorphism you build out of this H5. Conversely, I should say this is free and proper. Any free and proper actor from G onto H gives a star homomorphism satisfying the above conditions. So in the particular case where, well, for groupoids and actors, we showed that, well, there is a functor going from the groupoids up to C-star algebras where an actor gets turned into a star homomorphism. And in the case where your groupoids are effective and your star homomorphism preserves a bit of the structure intrinsic to the groupoid, you can actually go the other way. You can go back down. The corollary to this, the category of Cartan pairs. In quotes, because I haven't told you exactly what the morphisms are, but they're these guys. Is equivalent to the category of twisted groupoids, effective groupoids with actors.
So is it more than naively you would think, oh, just preserving the Cartan pair like this, because the map which takes the Cartan would be enough. But this is quite a bit stronger, right?
It is stronger, yes. It's not enough. I'm pretty sure it's not enough to just preserve. It's definitely not enough to preserve the subalgebra alone. If you preserve the subalgebra and intertwine the conditional expectation, actually, if you intertwine the conditional expectation,
I would suspect not. I suspect that the middle condition is also important.
the middle condition is definitely important, but is also the finickiest. But this is, on the groupoid side, this is the thing that lets you really construct the actor on the underlying groupoids. So the construction of the Lenoir reconstruction of a groupoid from a Cartan pair is quite constructive. It's just that, it's constructive. And then with that exact structure, that's heavily used to be able to rebuild this actor down here between the underlying groupoids. You have to go via the Lenoir reconstruction. I don't know another way to do it.
So it's an example of like what you said if you preserve the diagonals, but not the other stuff. Like that there's no, it doesn't come from.
I think there is actually. I think even on maps on like 4x4 matrices, you can create sort of examples.
Yeah.
Which do this, right?
You would need some. You just need, if on like the matrix examples, you just need to preserve the diagonal. But preserving normalizers is saying that every matrix with exactly one non-zero entry in each row and column has to also be mapped to a matrix with the same properties.
There's monomial matrices. So.
Yeah.
But then, so for isomorphisms, it's enough to just preserve the Cartan, or for isomorphisms?
For isomorphisms, it's enough to just preserve the subalgebra. And this is because for an isomorphism, and in general for a surjection, you will automatically intertwine the conditional expectation, because the conditional expectation is actually unique. Not surjections, ejections. One of the two. Can't remember which one. I'm getting my left-right confusion now.
Yeah.
But certainly for isomorphisms, that is automatic if you preserve the subalgebra. Because you can go, there's two things to go. Yeah. And you know that this map is unique, having these properties, and both of these do it, which makes it automatic. As for explicit examples of things that don't map normalizers to normalizers, I haven't really thought about them because I've been able to build more examples of things that do just by simply taking actors and then lifting them to the C-star level. On the groupoid level, this means that you take, if you have a function that's supported on an open bisection, which we haven't defined, but you know what it is. A function that's supported on an open bisection in the domain will get pushed over to a function supported on a bisection in the codomain. So you have this ability to preserve bisectionness. So.
When it is then, there is an access, but the then is not said to be free here.
Well, then there is a free proper actor. Yeah.
Obviously.
Yeah. So this I mentioned before. Let's see it. The actor is free if and only if it intertwines the conditional expectations. And so this condition here ensures that it's free anyway. And then properness just comes from the fact that it lands in the subalgebra and not in multipliers on it.
Okay, but the properness is just sufficient condition.
Properness is also necessary because otherwise we would land in there.
Okay, so it's also.
Yeah. Yeah, that was pretty much what I wanted to talk about. So thank you very much for your attention.
So you start with like full groupoid systems, right? And then at some point you switch to the read response because I guess that's where Reynolds reconstruction.
Yeah.
Do you know? Is there also a reconstruction theory for full, like to get like full? Or like as a first step, if you take an effective groupoid and you take its full root system, is the diagonal like is that a Cartan?
It's not a. It's sometimes a Cartan for stupid reasons. The stupid reason being that the full and the reduced happen to be the same sometimes, and in that setting, yes. But in general, you would need different slight, or at least something to replace the conditional expectation, because the conditional expectation being faithful is exactly what says that you're in the reduced. Yeah. And if you don't have faithfulness, you can't reconstruct this star homomorphism in the same way. This Reynolds evaluation method in the same way.
I mean, in the paper that I have recently with Lisa, Ben, and Kevin Comic, we do it also for the full, like for anything in between. It's just as John said, if you just don't require the expectation to be faithful, you can actually with the work show that it will still be faithful on a dense suburb, and that's enough to still give you a reconstruction. Yeah. I mean, I haven't thought about reconstructing morphisms, but just for actually reconstructing the group itself. Yeah, you can do it with the full as well.
You might be able to actually for morphisms, and as well, now that I think about it, I guess it was just more I was scared off by the fact that no one, well, this was before the paper that of yours came out, and so I hadn't really seen people considering the full side of things. But you might be able to do it.
Yeah, speaking of.
Yeah. The other thing is that I suspect that actors have in like this Cartan semigroups situation, there is a very strong relationship between actors and semigroup homomorphisms with some extra niceness.
Yeah. Well, I mean, the middle condition you had before, I was preserving the semigroup. So yeah.
Yeah, exactly. And it will be a semigroup homomorphism because obviously it's a star homomorphism. Yeah. But in general, if you have a regular master inclusion, you can show that it has to, there's like another slightly more groupoid theoretic way to show that it must come from, well, I don't know if it's more groupoid theoretic than what you do, but there is a way to show that it comes from, it's some exotic completion of the biogroupoid C-star algebra.
Okay. Yeah, I mean, the stuff we're doing is definitely not masters, right? As soon as it is effective, the canonical semi-Cartan is no longer a maximum.
I was able to do it using some kind of this weird construction of pseudo expectations, stuff like that in the non-Hausdorff setting. In particular, it works in the Hausdorff setting, but it was surprisingly not obvious how to do it. But it's in there's at least part of it in this paper of mine that is currently under revision but it's on the archive. It's a central Cartan subalgebra paper.
So if G and H are just groups,
yep.
Does this tell you something about maps between the group C-star algebras that tells about its properties? Do they come from essentially group actions?
This reconstruction doesn't work because groups are never effective.
I see.
However, you can just ask what are the morphisms coming from actors. That an actor between groups just boils down to being a group homomorphism.
Right.
And freeness boils down to injectivity of that group homomorphism.
Right.
So all you get really is just a group embedded into another group, and this induces an embedding of the C-star algebras.
This, I guess, is very few of the possible maps between the group C-star algebras.
Yes. It would. I mean, even just on the level of isomorphisms, it's not necessarily true that every isomorphism of a group C-star algebra comes from an isomorphism of a group. Maybe there's some very, very rigid groups like Z mod 2.
I'll work with this.
No, Z mod 2 doesn't work. Even Z mod 2 doesn't work.
Okay, groups doesn't work. Group bundles are effective.
Group bundles are the opposite of effective. Group bundles are only isotropic. Every element of the group bundle that it has range and sorting.
It's exactly the opposite. So
yeah. So this property, if you take in the example of the if you have a transformation groupoid, effective is equivalent to topological freeness of the action.
Yes. And
This just says that there is a dense set of points that get moved around by each group element.
and then we know that when there exists Cartan preserving isomorphism between them, when the actions are orbital equivalent.
Yes. I believe so.
Yes.
So this is, but that just comes from the level of the transformation groupoids being isomorphic.
Yeah,
And two isomorphic groupoids will give you two isomorphic groupoid C-star algebras. That was.
But it's not Cartan preserving. For the Cartan
If the isomorphism, no, for the groupoids it is, because the isomorphism of the groupoids has to preserve the unit spaces.
Yes, in the level of the group.
Yeah. But you could have an isomorphism of, for instance, if you take just the very classical first example. Oh, right, this is S1, so we don't use this group. You take the group C-star algebra of the integers, which you don't need to put the reduced there because it's going to be an amenable group. This is isomorphic via the Fourier transform to the functions on the circle. And there are two groupoid models for this. One is just the circle by itself as a topological space. And the other is just Z as a group. And so the reason that you don't get an intertwining of the Cartan-like subalgebras is because, well, this thing doesn't have a Cartan subalgebra, but if it did, the functions on the unit space is just a copy of C. Whereas it's not clear, well, there's a canonical choice of which copy of C to pick out here, and then you have to pick out the unit in here, then you just have a unital star homomorphism. You don't really learn more from preserving this subalgebra. It's fine.
I have one sort of question. Like, so,
Yeah.
so you did mention the end, like, oh, I don't want to deal with twists, so I'm just going to assume that we don't.
Yeah.
Could there actually be any characterization of like the C-star algebras, the Cartan pairs that come from non-twisted groupoid C-star?
This is something that I've been asked a couple of times, and I've also asked people who are smarter than me. And the only kind of solid piece of anything that I've seen to gotten as an answer has been that it's certainly necessary for the Cartan reconstruction to include twists, because a groupoid C-star algebra is always isomorphic to its opposite C-star algebra, where you just take the same, all of the structure except for the multiplication, you just reverse it. But this is not true for twists.
Well, are there non-trivially twisted groupoid C-star algebras which are still isomorphic to those?
Maybe. You can get some weird stuff with stable rank as well. Xin Li and Aliraj have a paper where they compute some stuff, some stable rank of inductive limit C-star algebras, these AH algebras, including some of the Villerton algebras, which are some of these first examples of things that satisfy a lot of the adjectives for the classification program, but not Z stability. And they show that over the same groupoid, by changing the twist alone, you can achieve any stable rank number you like. So without the twist, it's stable rank 1, these C-star algebras, which stable rank is a kind of dimension theory for C-star algebras in a certain sense, along with the 50 billion other dimension theories for C-star algebras. But you can get any stable rank 1, 2, 3, 4, 5, 6 up to however high you like, and also infinity by changing the twist alone.
So I mean, this is in Villerton's paper. He does this. So do the twists correspond to the?
I don't know. So he definitely constructs the counterexamples. That the new thing is that it only comes from changing the twist.
Right.
Yeah. Right. So certainly the counterexamples exist beforehand. It was just not necessarily on the group level. I think. Is there? It was something to do with the twist. What was the exact question?
Could there be some nice characterization
Ah,
of the Cartan pairs which don't involve the twist, which don't need to involve?
Can you, in the reconstruction theorem, can you get rid of the twist?
Yeah, just by placing some restriction on the Cartan pairs. I don't know what it would be.
It's not obvious to me. I'd really like that. That would be very
It
nice.
would make giving these sort of easier.
I dislike the twists with a great fervor.
Is there
So
a,
what,
sorry,
no,
is there a one-line version of this kind of theorem or this kind of theory?
For that part, I'm not sure. Definitely for the Cartan structure, there's the Feldman-Moore stuff. But the actors, I guess it should just work. You might need to replace the word continuous with the word measurable everywhere. But
I think they always dealt with like co-cycle twists, but I think because
yeah, you only have to deal with co-cycle twists because you can always take measurable sections of your line bundle.
yeah, you can always cut them up, but in the C-side zone you can't just cut them.
Yeah, right. Okay, so that sounds positive, but it should.
Well, there's still a twist. There's still this co-cycle, but
Yeah. But they also only consider equivalence relation groupoids as in the principal case, which then puts a lot of structure on. If you have an actor on or from a principal groupoid, the structure is almost or to a principal groupoid, one of the two. A lot of the structure is determined by the anchor map alone, because the anchor map gives you conditions on where certain arrows must start and end. And in a principal groupoid, this is all of the information you need to define the arrow within the groupoid.
and so you have the twist version of the story?
There is a twisted version, yes. There is also a non-household version.
Okay.
I guess it's probably maybe saving questions for the pub. But yes, thanks again.
That's what the change.
Question, I think you might be able to-